Hello, everyone. This is going to be the start of our semester of videos for CH430A or Thermodynamics and Kinetics. This is your host, Dr. Mir, and it will be my job to guide you through these videos, through this material via these videos for the semester. And so today, kind of what I want to do is try to give you an overview of what is physical chemistry and some of the details of measurement, because measurement is very important to P-chemists. So in P-Chem, we really have three main topics of study. There's thermodynamics, kinetics, and quantum mechanics. And in this semester, we are going to be focusing on thermo and kinetics. Quantum mechanics, that is next semester. So, what are these? Thermodynamics is really the study of the energy involved with reactions. So, in thermo, we want to find out how exothermic is this reaction? How endothermic? For this reaction to happen, how much energy do I have to add? Or how much energy do I get out? Kinetics is the next field that we're going to really study this semester. And kinetics is less worried about the energy, but more about the speed. Now, the energetics of a reaction is involved with dictating the speed of the reaction, but kinetics really asks how fast. Then quantum mechanics studies the energy of electrons and orbitals. And so quantum mechanics is really saying, electron, where are you and what is your energy? Physical chemists try to understand how and why chemistry occurs. So thermo really investigates the flow of energy in reactions. It tries to answer how much energy is involved in a reaction and how much energy drives or doesn't drive a reaction. I'll edit my slides as we go. Within thermo, there are two large segments. There's statistical mechanics, which is really understanding the energetics of a single molecule and trying to scale that up to arrive at bulk properties. And then there's what I like to call classical thermodynamics, which is measuring and understanding the energetics of bulk solutions. So the difference between these, statistical mechanics starts with a single molecule, and we work our way up. Because we say that if we can understand the energy involved in a single molecule, that then we can figure out the energy involved in a mole of molecules. Whereas thermo, classical thermo, really measures solutions or large scale samples. And by large, I just mean not a single molecule. Kinetics tries to figure out the speed. So it answers things like how fast is a reaction. It also goes into what is the mechanism for the reaction. And mechanisms are something that you typically think about with organic chemistry, but it turns out that a lot of P-chemists are really interested in mechanisms as well. And P-chemists go a step further beyond the organic chemists for us, it's not enough just to know the mechanism, but we want to know why. How do we know? And really think about complex reactions that don't really have a predictable understanding from the from the organic chemistry perspective. So next semester is quantum mechanics, and this is really investigating the location and the energy of electrons within an atom, which is what physicists are most interested in, or molecules, and chemists like things a little bigger, not huge, but a little bigger. And so quantum mechanicists, we try to answer how does the electron configuration, geometry, and other properties of a molecule dictate the energy or speed of a reaction. And so quantum mechanics is kind of the backbone and the guiding and the motivation for both kinetics and thermodynamics. So someone who gets a PhD in physical chemistry, like me or Dr. Jean, our graduate coursework covers advanced quantum mechanics, advanced thermodynamics, and advanced kinetics. And so we really take a deep dive into these three topics and how these three topics are very interrelated. So this semester, we're going to start with statistical mechanics. This is in chapters really 2 through 6. I added 1 in there because that's kind of the intro backbone to the entire semester. In this, we really want to figure out how to relate the energy of individual molecules to the properties demonstrated by a large collection of sample. And we want to deeply understand, explain, and use temperature in its relationship to the energetics of molecules. From there, we'll move into our second unit, which is thermodynamics. That's in chapters 7 through 10 in your book. And this is really to determine the energy-related driving forces for reactions and phase changes. So we want to understand how things are changing. Kinetics, this is going to be at the end of the semester. And in kinetics, we're going to cover chapters 12 through 14. And this is where we want to describe rates, mechanisms, and driving forces for the reactions. Okay, so I've been talking about how physical chemists like to study reactions. Now, we also study individual molecules, but oftentimes our starting point with individual molecules is so that we can combine them and understand a reaction. And we do this via experimentation. And yes, even theoretical physical chemists, so these are the physical chemists who spend a lot of time deriving these equations and working on creating computer programs to be able to do some very complex calculations. Even these theoretical physical chemists use experiments. And these experiments are used to determine the fundamental properties of species or reactions that are studied. But our challenge is that there are only 2 direct measurements. All other properties are derivations from these. So we can directly measure distance and time. Everything else is some combination of those measurements. Okay, so let's go through the PChemist text toolbox. So we have things like volume. The symbol we give volume is V. The SI unit is a cubic meter or 1,000 liters. That's huge. Think about the size of a 2-liter soda bottle. Yeah, you've got about 500 2-liter soda bottles to get 1 cubic meter. That's a lot. So oftentimes we use liters, milliliters, centimeters cubed as common units. And something useful to know is that 1 milliliter is equal to 1 cubic centimeter. And if you are in medicine, that is the same thing as 1 cc. Mass, the SI unit is kilograms, but we like to measure in grams and milligrams because it's rare that we have a full kilogram of anything. Moles, Well, it's a mole. And this is your reminder about Avogadro's number. And remember that a mole is just a count of how many things you have. And and 1 mole is equal to 6.022 times 10 to the 23 anything. We often give this the symbol capital N with a subscript A. Molar mass. In our textbook, we get the scripty M. It actually looks like this, but my slide making fonts don't have that M. But whenever you see this M in your textbook, it is molar mass. Molar mass, the SI unit is kilograms per mole, but we like to measure this in AMUs or grams per mole. And we can get the number of things by taking the mass, the number in moles, by taking the mass and dividing it by the molar mass. I know it's been a while, but I'm sure that will come back to you. Pressure is measured in a Pascal as the SI unit, which is a weird unit. But there are many other units that we like to use, like atmospheres, millimeters of mercury, bar, coulomb. I recommend look up the conversions. I do not expect you to memorize these. Look them up. Pressure is defined as force divided by area. And force is just like force that you have from physics, the force that you know from physics. So gravity, force. Temperature, T, the SI unit is Kelvin. We often like to measure in degrees Celsius. And here is our handy dandy conversion between Celsius and Kelvin. Okay, I recommend holding on to this list. You can find this list in more descriptions of these in chapter 1, section 1 of your textbook, to really kind of get a sense of how do we measure something like pressure using just our clock and our ruler. So in PChem, there are really 2 more very useful and necessary units. One of these is energy. Energy is the SI unit is a joule, given the symbol J. And the energy is really governed by the first law of thermodynamics, where our change of energy and this delta we're going to use a lot is going to be our final condition minus our initial condition. And it is equal to Q, which is heat, plus W, which is work. And we will, in kind of our second unit, we will go into this in detail. Entropy is the other big measurement that PChemists need to use. Entropy really helps us define temperature. And entropy is, we call it a measure of the disorder of a sample. And we are going to go into entropy and a lot of definitions of entropy. It's going to be one of the key points of the semester. The SI unit is a joule per Kelvin times mole. And we really need entropy because entropy defines temperature. And so the change, this is the derivative symbol or change of the energy of a sample with respect to entropy, as long as we are holding volume and moles constant, will give us a definition of temperature. And we are going to go a lot more in depth on this sort of calculus view and definition of things and what it means and how we use it. And that's something we're going to work on throughout the semester. So don't worry that this is a little foreign right now. We will get there. Okay, so every one of these videos is going to end with a now try this problem or couple of problems. These are for you to practice and check yourself, to check your understanding. The quizzes that you have each week are going to be based off of these now try this problem. I will never ask you something that hasn't been a topic that hasn't been covered in a now try this. And those quizzes will have questions at the same level of difficulty as the now try this problem. So you have 2 for today. And once you convince yourself that you understand these, you can check yourself with the answer key on World Class. Okay, so stay tuned. In our next discussion, we're going to start into the kinetic molecular theory of gases, which is section 1.3 in your textbook. So I'll see you for the next video.